Hi, I'm Ben-Yaakov. The title of this presentation is Design of Resonant LLC Converters by Scaled Cloning. Let me first explain the motivation and objective of this presentation. The design of LLC converters is really complex because there are so many degrees of freedom. And the design usually applies many rules of thumb and takes a lot of experience to design a good converter. Now, good designs are available as prior design, that is something that you have done sometime before, and in application notes and reference designs. Now, the available designs, however, may not be exactly what you need for a given project. That is, for your project, you may need another output voltage or input voltage or frequency, so that you have really to modify the design that you have to meet the specific requirement on hand. So this presentation shows how, in a very simple way, you can translate a, so to speak, good design to another converter that will meet specifications in terms of switching frequency, power level, input voltage, and output voltage. Now, a resonant LLC converter is built around a resonant network that includes two inductors, L sub R and L sub M. L sub M is usually part of the transformer, actually the magnetization inductance of the transformer. And this network is driven by a bridge, in this case, to form a square wave. Now, the output is coupled by a transformer, and there is a rectifier, in this case a bridge rectifier, and a load. So we generate a square wave here, there is a resonant current, a voltage is transferred, and the current is fed to the output, which is, of course, DC here. Now, there is another possibility, of course, and that is the half bridge. In this case, we have only two transistors. This is the waveform we are going to have. They have a DC component, but due to this capacitor, we really don't see it in this network. And the output, again, is coupled by a transformer, rectifier, and a load. Now, for design purpose and analysis and simulation, it is very useful to use a sort of a equivalent circuit, an AC equivalent circuit, in which we assume an AC drive rather than a square wave. We have the resonant network, and then we would like to replace the rectifier and filter by a linear resistor, which will be easier for a linear analysis, like AC simulation. Okay, so how can we do this? In 1988, Professor Steigerwald showed that you can replace the whole rectifier plus load plus filter plus load by an RAC, an equivalent RAC. This will be the secondary side. And without going into all the details, the value of this RAC is related to the actual value of the load, the DC load resistor, and by a factor of 8 over pi squared, so 0.8 approximate. Okay, so instead of having the full bridge with all the square waves, etc., and rectifier, we can replace it by this circuit, and we can go one step farther. We can reflect this secondary side resistor into the primary side, reflecting it through this transformer, and of course defining the turn ratios n to 1. N is the primary, 1 is the secondary. Then we are going to see from the primary side a resistor which is n squared times the secondary resistance. So plugging in the Steigerwald relationship, we get that this RAC reflected to the primary is n squared 8 over pi square RL. So we can replace a resonant LLC converter by an equivalent AC circuit that looks like this. We have an inductor, another inductor, capacitor, plus our AC, which is the reflected value of the load. Now VAC represents the drive. Now originally we do have a square wave, okay? So we use the so-called first harmonic approximation. That is, since we have a resonant circuit, which is it's a tuned circuit and it looks at frequencies around the resonant frequency, the most important component of this waveform is the first harmonic. So we can, in the case of a full wave drive, we have a plus minus V in square wave. So this is the amplitude. Now we multiply it by 4 over pi. This is the conversion to the first harmonic of this square wave waveform. And if I want it in RMS units, then I have to divide it by square root of 2. Now in the case of a half bridge, V in is the full span here. However, effectively, we have an AC which is only plus minus V in over 2. So the AC equivalent will be V in divided by 2, and then again to get the first harmonic, and then square root of 2, we have the RMS value. So by this we're getting the equivalent AC source that is feeding the converter. So let's first have a look at one simple case, and then we'll go to other cases. So suppose we have a good resonant LLC converter design. That is something that we are happy with, but it is designed for some specific case of input voltage, output voltage, etc. Now suppose we would like to change the output voltage, that is the nominal output voltage, from a certain value, VO1 to VO2. Everything else is assumed to be the same, that is power, switching frequency, etc. So in this case, we'll have to change two things. We'll have to change the transformer ratio, and we'll have to change the nominal equivalent load, because if the voltage is changing, then for the same power, clearly you will have another load. So since the voltages are related by the turns ratio, N again is 1 to N is the transformer turns ratio, N1 is the original, N2 is the new one that you need. So the new one that you need will be the original N1 times VO1 over VO2. VO1 is the original one, VO2 is what you'd like to have. Now, since power is V squared over R, then it turns out that the new nominal load will be the old one times voltage ratio. This is the one that you want, this is the original one, squared. So this will be a solution to the case that you'd like to leave the converter as it is as far as power, input voltage, frequency, but you'd like to change the output voltage. Okay, let's move now to another case. In this case, we would like to change the frequency. Again, we assume that we want to leave the power, input and output voltages the same, but we want to change the frequency. Now, in general, the quality factor in a parallel resonant circuit is R over omega L. So since we have to keep the Q the same, R the same, then when we express these for the two cases before and after change, we come up with this relationship which says that the new value of inductance is the old one times F1 over F2. F1 is the original frequency, F2 is the one that you need. Since Q can be also defined as R over the characteristic impedance, which is square root of L over C, well, it turns out that, again, if I'll divide the two cases before and after the change, this is the ratio I'm getting between the capacitor and the inductor, and to sum up, what we are getting is the following. To change frequency from F1 to F2, you have to change the capacitor from the original multiplied by F1 over F2. You have to change LM, original, times F1 over F2. And of course, LR2 will follow the same rule. That is the original times F1 over F2. Okay, let's move now to another case. Suppose we have a good design and we want to change only the power level, the nominal power level. That is, everything is the same, input voltage, output voltage, etc., and frequency, and we want to change just the power level. So starting with the relationship of power, which is V squared over RAC, this is the voltage on the RAC equivalent resistance. We get to this relationship when we divide it for the two cases, and again applying the definition of the quality factor, we get this relationship, and again we get an expression for L2 when, of course, F, the frequency, is 1 over 2 pi square root of LC. To sum up, in this case, C2, the new C2 is C1 over P2 over P1. LR2 is LR1 times P1 over P2. Notice that this is the inverse because the product should be the same since we are keeping the frequency. And same thing goes for LM2, which is LM1, the original one, P1 over P2. Another case. Suppose we like to keep everything as it is, but to change V in, that is, we have a certain input voltage, we want to work at another input voltage, keeping the power, switching frequency, output voltage, everything else the same. Starting with the relationship of power, which is V squared, this is V across RAC over RAC, and then since the RAC is always a fraction of V in, and it is be the same fraction for the two cases, so power will be K squared times V in squared over RAC. Now I take it for the two cases, before and after, dividing it out, and again, without going into all the details, here are the results we are getting. RAC new is the original RAC times V in 2, V in 1 squared. V in 2 is the new input voltage, V in 1 is the old one. C2 is C1, the original one, times this ratio squared, V in over V in 1 over V in 2. LM2 is LM1 times this ratio. Again, it's inversed so that the product is constant so that we have the same frequency. And of course, LR2 is following the same relationship. Let me move now to the last case that I'm considering it. Suppose we have a good resonant LLC, but it is operating in full bridge, but I like to operate it in half bridge. Now, when you operate the converter from a half bridge, then the actual square wave is half the voltage. So, in fact, you can say that you can consider the two cases, that is the full bridge before and half bridge after the change, you can consider the two cases as if they were full bridge, except that you moved from an input voltage of V1 to an input voltage of V2 over 2. V2 is the voltage of the half bridge, but the full bridge equivalent is V2 over 2. So it's a case of changing the input voltage, which we have discussed earlier, and you can follow this procedure. So this actually brings me to the end of this short presentation. I thank you very much for your attention. I hope you found it interesting and that it will be useful to you in the future. Thank you.